How's exam 3?
It's fun.
Yeah, I expect it was fun.
It was an adventure.
Yeah, I'd say.
You should get this back in a couple days. And the bonus quiz.
You don't get on.
All right. Chapter 23, main intent. How can we establish a basis for rationalizing strengths of Bronsted-Lowry acids and bases? What you will see is that we will assemble a collection of factors which apply to rationalization of effective negative charge density for the Bronsted base. Because as we recognize from conjugate theory, when you know the strength of a Bronsted base, you now know the strength, relatively speaking, of its corresponding conjugate acid. So if we can distinguish between the strengths of two bases, we immediately then have distinguished between the strengths of the corresponding conjugate acids. Now, you will see that we will assemble a number of factors. But for each particular case, all the factors will not apply. You're going to have to make decisions. Which factors apply? And then select those factors to support your argument. Your rationale for the basis of assessment of effective negative charge density. So you got to develop a good ability to make judgments and decisions. Hey, that's what the game is always about. I don't care what you're involved in life. If it's a position of responsibility, you got to make decisions. You got to make good judgments. If you're the boss and you issue a set of directives to the people who work for you, and they carry out your directives, and the job comes out fouled up, they're not the ones who are in trouble. It's the one who gave the bad directives. Now, as we said, here's what we're going to do. What did we consider so far? Stabilization of negative charge density based on charge to size ratio. If, with all other factors being equal except size, we have an anion with a charge of -1. That's this big. Compared to an anion with a charge of -1, that's a whole lot smaller. No other factors apply except charge to size ratio. The smaller anion has the higher negative charge density. And the higher the negative charge density, the more strongly H plus is attracted. Which means the acid derived from the smaller anion will be a weaker acid than the acid derived from the larger anion. Now, what if the anions in consideration are the same size? In many cases, this will be what we'll find. Not exactly the same size, but very close. For example, monatomic anions derived from period 2 atoms, which are neighboring atoms, are going to be close to each other in size. But there will also be an appreciable difference in the electronegativities of the parent atoms. Fluorine, for example, 4.0 versus 3.5 for oxygen versus 3.0 for nitrogen. And we can continue right to left for the period 2 atoms, recognizing that between each neighboring pair there's a difference of 0.5 electronegativity units. So, if I got two anions that are about the same size, Assessment of effective negative charge density based on charge to size ratio will hardly be the distinguishing factor. But if one of the anions is derived from an atom that's much more electronegative than the other anion, given that electronegativity is a negative charge density stabilizing factor, the anion derived from the atom of greater electronegativity will be the weaker or stronger base.
Strong.
Weaker or stronger? I got two anions. They're the same size. One anion is derived from an atom of greater electronegativity than the other. Which anion will have the greater effective negative charge density? The anion derived from the atom of greater electronegativity, or the anion derived from the atom of smaller electronegativity? Which anion has the greater effective negative charge density? Remember, electronegativity is a property of a species which stabilizes negative charge density. That makes the negative charge density peaceful and unreactive. It decreases effective negative charge density. Well, keep your mind on that, because we'll look at some specific cases in just a moment. In family acids, we've talked about HF and HCl, at least from an absolute strength standpoint. And in our acid-base table, note that HCl is a strong acid categorically, whereas HF is a weak acid. So if, from that comparison of strengths, we establish a periodic pattern, would you be surprised if you find HBr to be a stronger acid than HCl? Since as we go down the family, we found out that acid HCl is a stronger acid than HF. And HI is even a stronger acid than HBr. Just paying attention to periodic patterns, periodic trends, which you talked about in 2045. So the relative acid strengths of these four acids, which are derived from in-family elements to halogens. HI the strongest, HF the weakest. All right? Now let's make a comparison of acid strengths for acids derived from atoms related to each other by being derived from elements in the same period. HF from fluorine, H2O from oxygen, ammonia, H3N from nitrogen, and methane molecule, H4C from carbon. CNOF, all neighbors of each other in period number 2. Now we have not talked about the acid strength of methane. We can infer that the acid strength of ammonia, whatever it is, must be weak, because in our acid-base chemistry, we find ammonia listed in the base column but not in the acid column. But we know about the relative acid strengths of these two. This is a weak acid, but this is much weaker. So if we again establish a periodic pattern, a periodic trend, given that HF derived from fluorine is a stronger acid than H2O derived from oxygen, we shouldn't be surprised to find out the acidity of water to be greater than that of ammonia. In turn, the acidity of ammonia be greater than that of methane. That doesn't mean these have any considerable acid strengths at all. We're establishing a pattern of relative strengths, not absolute strengths. We're not saying anything is strong or weak. We're saying stronger or weaker. Now, after recognizing that HCl is a strong acid, if these acids are stronger, clearly they too are strong acids. Now, we look at the anions. Based on the acid strengths, these have got to be the base strengths. This base, the stronger of the halide ion, the strongest of the halide ion bases. And for the in-period acids, this is the strongest base. So now we ask the $64 question. Why? What rationale can we apply to explain this pattern of base strengths? Well, The size considerations which we made at the start of chapter 23, which I did to serve this purpose really, showed us. As we go from atom to atom inside a family, for A family atoms, we generally observe a substantial increase in size as you go from period to period. Chlorine a lot bigger than fluorine. Bromine a lot bigger than chlorine, etc. Okay? However, for the parent atoms, fluorine, chlorine, bromine, iodine, how do the electronegativities compare? Well, we know fluorine's number 1 in electronegativity, and we know pattern-wise electronegativities decrease as you go from top of the family to bottom of the family. So fluorine is the most electronegative element, and the most electronegative, clearly the most electronegative halogen. Chlorine is number 2, bromine is number 3, and iodine is number 4. The numbers are, if you're interested, 4.0, 3.0, 2.8, and then 2.5, if my memory's right, for iodine. So we're not seeing too much difference in electronegativity for chlorine, bromine, iodine. But think about this. If I wanted to decide on the relative base strengths, the relative effective negative charge densities of these 4 bases, depending upon electronegativity, which of these bases would I expect to be the weakest and most stable? Which one is derived from the atom of greatest electronegativity? Fluoride ion. So on that basis, I'd expect fluoride ion to be the weakest, most stable, least reactive of these bases, which would make HF the strongest of these halogen acids. Is that true? No. So, we're talking here about making good decisions. We recognize, if I want to try to rationalize this trend in base strengths as a consequence of atomic electronegativity, my argument falls flat. Because that argument would predict this is the weakest and most stable base, and that's not true, because we find this to be the most reactive of these 4. This is the strongest base of these 4. This has the greatest effective negative charge density of these 4. That's why HF is the weakest acid. Now let's try this from a charge to size ratio standpoint. Fluoride ion, chloride ion, bromide ion, iodide ion. Big increase in size as we go from fluoride to iodide. And they're all -1. So this tells me the effective negative charge density of fluoride ion is certainly the greatest for the halide anions, as a consequence of charge to size ratio. That makes fluoride ion the strongest base, which in turn makes HF the weakest acid. Is that true? Is that the facts? Yep, that's the facts. So that's the argument we pick. Right? Call it factor number 1 if you want. Now let's look at the second pattern. The in-period acids, and corresponding pattern in the bases derived from these in-period acids. Again, if this is the trend in acid strength, then this must be the trend in base strength. Which of these anions is the largest? That should be ever so obvious. If I just look at the atoms from which these species are derived, carbon, nitrogen, oxygen, fluorine. Of these 4 atoms, fluorine is the smallest and carbon is the largest. Okay so far? And clearly, if I add 3 hydrogen atoms to make this anion, to only 2 here, 1 here, none here, this has got to be the largest of these anions. Right? But do you think there's much transfer of negative charge density for this anion to these atoms? Do these atoms have appreciable electronegativity? How does the electronegativity of hydrogen compare to carbon?
Pretty close.
Tell me more.
0.4 off.
0.4 difference. Which atom is of the greater electronegativity?
Carbon.
Carbon, electronegativity 2.5, hydrogen 2.1. So I don't expect any inductive stabilization of this negative charge density at all by hydrogen. The negative charge density is principally centered on carbon. Here on nitrogen, here on oxygen, and obviously on fluorine. So based on charge to size ratio, this is the largest of these anions. This is the smallest. Based on charge to size ratio, which of these would I expect to be the strongest base? Based on charge to size ratio.
H3C.
Which one is smallest? Fluoride ion. And they're each -1. So based on charge to size ratio, I expect this to have the fill in the blank, greatest or smallest negative charge density? Greatest. It's smallest. Does that fit the facts? Is this the strongest base? No. So forget the application of factor number 1 to rationalize this pattern. So you got to learn how to make good decisions here. All right? Now let's consider electronegativity. Fluorine 4.0, oxygen 3.5, nitrogen 3.0, carbon 2.5. A pretty fair difference in electronegativity for the parent atoms, the principal atoms of these anions. And we've recognized there's no induction stabilization of negative charge by hydrogens because they're of lower electronegativity than the atom to which they are covalently connected for these species which contain hydrogens. So based on electronegativity, I expect this to stabilize its negative charge density most effectively. That makes this the weakest or strongest base? Say again. You're stabilizing negative charge density by electronegativity. That makes the negative charge density stable, not reactive. Makes this a stable base. Does that fit the facts? Yep, that fits the facts. Now one more consideration. Is there much difference in size between these two? Particularly given that the hydrogen atom components of this, and this don't really mean anything because they don't support drain of negative charge density by induction because their electronegativities are smaller than that of the atom to which they're covalently connected. So if I look at this versus this versus this, do I expect to find much difference in size? These are all atoms from the same period, aren't they? And neighboring atoms in the same period aren't much different in size. Hardly like you find for the halogen atoms, big difference in size. So what do we recognize? If for the atoms, for the species in question, there's a big difference in size, this is the factor likely which will explain base strength and corresponding strength of conjugate acid. But if sizes are about the same for the species in consideration, like we have here, then this is what counts, electronegativity. All right? Now then, so we'll rewrite these up here. Two factors in our assembly. So if you look on page 2331, You'll see that the next factor to be considered is induction, which we've already talked about. Now I've shorthanded the word induction, but let's take a look at a case. To show you more about induction in operation. This acid look familiar? What is it? Acetic acid. Our shorthand reference is HAC. So, with that as a given, I don't think you'll be surprised to find that the name of this is trichloroacetic acid. And this is trifluoroacetic acid. All right? Now clearly, when trifluoroacetic acid and trichloroacetic acid behave as acids, since they only have one hydrogen atom in their molecular composition, the only thing that can do to behave as acid is lose this H as H+. That makes this. Here, this. And earlier on, we talked about the behavior of molecules like acetic acid. Do you expect these hydrogens to be liberated as H+ by the acetic acid molecule? Do you think these hydrogens are found to be acidic hydrogens, lost as H+? We haven't found that to be the case, have we? Notice that if one of these hydrogens leaves as H+, and you're going to put a minus charge on carbon, is that a stable minus charge? What do we find out over here? This is the most reactive of these bases because the electronegativity of carbon is fairly small and doesn't stabilize this negative charge density much at all. That's why this damn thing is reactive. Again, we did a couple cases like this way back in chapter 18. On the other hand, if this hydrogen is lost as H+, we create a minus charge on oxygen. Is that more reasonable? Why? Why is it much more reasonable to create a minus charge on oxygen than it is to create a minus charge on carbon? Much more electronegative atom. Stabilizes negative charge density much more effectively. So now we know why acetic acid, in behaving as an acid, loses one H+ per molecule. That's it. It never loses any of these carbon-bound hydrogens as H+. Now look at these three bases we got on the board. In each case, we've got a minus charge on an oxygen atom. An oxygen atom which is covalently connected to carbon, which is doubly bonded to an oxygen and then singly bonded to another carbon. Okay? Well, look at each of these anions from this standpoint. How do they compare? If we don't pay attention to the atoms which are connected to this peripheral, to this carbon atom, these peripheral atoms which are connected to this carbon atom, how do these bases compare compositionally and structurally? They're exactly the same, aren't they? So tell me, if this negative charge stays on this oxygen, and this negative charge density is not affected by any other part of this anion. If this negative charge stays on this oxygen, not affected by any other atoms in this anion, this negative charge stays on this oxygen, not affected by any of the other atoms in this anion. How are these going to compare as bases, strength-wise? It'll be exactly the same. So the $64 question is, are these bases the same strength? Or do they differ? Well, to find out, we go to the laboratory, take the parent acids and measure pH for a water solution with them each at the same molarity. Or if you prefer, make a water solution of each of these anions and measure the pH. For a water solution of these anions, the strongest base at a particular molarity will show the highest pH. For the corresponding acids, the strongest acid will show the highest acidity and lowest pH at a particular molarity, whereas the weakest acid shows the the highest pH. It'll be lower than 7, but it'll still not be very low. You have any idea how these bases compare strength-wise? You do if you read this stuff in the notes. Which of these is the strongest base? There's AC minus. That's much stronger than this base, which in turn is stronger than this base. Good deal difference in strength here. So this fact, these bases are not the same strength. This is the weakest and most stable base. That's the strongest and most reactive base. Tells us, number one, that acetic acid is much weaker than trichloroacetic acid, which is weaker than trifluoroacetic acid. And it tells us, more importantly, that these atoms and these atoms exert a stabilizing effect on this negative charge density, which these atoms cannot. What is this stabilizing effect? It's called induction. It's as if by magic, these chlorine atoms, because of their appreciable electronegativity, given that you got 3 of them, it's like they reach through the covalent bond skeleton of this species and pull the negative charge this way. Well, these atoms are even more electronegative. So they'll do an even better job of pulling this negative charge toward themselves. And the more you smear this negative charge, the more you dilute it. The more you dilute the negative charge, the more stable becomes the base. The greater is the reduction of effective negative charge density. Does that account for why this is the most stable of these bases? You're daggone right. So that's induction. And we've given you data to indicate that induction is real. I mean, when I first saw this, I thought, this is like magic. It's not magic. Because bonds are all electric in nature. And electronegativity is really an electric stabilizing effect. So we shouldn't be too surprised at this when we start to pay serious attention to the stuff we've already considered. Hey. All right. So now we got number 3 factor. Okay. Now, 2321 is an extension of induction. For induction and covalent bond skeleton length. The data which I've looked at apply to trichloroacetic acid. So we'll go back to this. Now let's put it over here. And start with another CCl3 group. So this again is trichloroacetic acid. This is trichloropropionic acid. I don't care about organic nomenclature at this stage of the game. So I'm going to write down its name. Once we have the formulas before us, we have the information we really need. And we see that structurally these are very much alike. Compositionally, however, there's a difference. This has a CH2 group in between this carbon, to which we have the OH, where H is lost as H+, and these highly electronegative atoms, which by induction have shown they can stabilize negative charge density. Here, no CH2 group intermediate. Okay? This, of course, is the CH2 group. So, whoops. As we did before, we imagine the parent acids to convert to their conjugate bases by H+ loss. And we ask the $64 question. Are these bases the same strength? Well, I expect you would bet no, they're not the same strength, because clearly they're different bases. A lot of similarities, but they're still not the same. So, which base is stronger? Because the conjugate acid of that base is weaker. Which base is weaker? Conjugate acid of that base is stronger. This is trichloroacetic acid. I mean, the anion derived from trichloroacetic acid, and this is the anion derived from trichloropropionic acid. Again, I don't care about the names. I'm not writing that down. Okay? Now note, if these three chlorine atoms can still stabilize this negative charge density by induction as effectively as these chlorine atoms. If these chlorine atoms can stabilize that negative charge by induction as effectively as these chlorine atoms, which of these will be the more stable base and why? That'll be more stable. Why? Would you dilute the negative charge more effectively? Because you'd now be spreading this negative charge over a longer covalent bond skeleton? Yeah. Now let's look at the facts. This base is stronger, which means trichloroacetic acid is a stronger acid than trichloropropionic acid. This is the fact. This base is stronger. Question. Does it then appear that the ability for electronegative atoms, atoms of consequential electronegativity, to stabilize negative charge density by induction, does it seem to matter how close these atoms are to the negative charge? You betcha. Because the difference between these two species, based on chlorine atoms and proximity to negative charge, is these are one atom further removed. And the facts indicate that diminishes inductive stabilization a whole lot. Because not only is this base stronger than this base is a lot stronger than this base. Trichloroacetic acid is a lot stronger than trichloropropionic acid. So, induction and covalent bond skeleton length. Result? Induction depends heavily on proximity. What does that mean? Closeness of atoms of high En to site of minus charge. Okay? Now, that's factor number 4 in our bag of factors. And what this stands for? Orbital electronegativity. Okay? We've already talked about how this relates to stabilizing negative charge density. But at that time, we were not into this topic on a specific basis. So let's take another look at orbital electronegativity. This is the ethane molecule, compact formula C2H6. This is the ethylene molecule, compact formula C2H4. And this is the ethyne molecule, also known as acetylene. You heard of acetylene? Common fuel. Compact formula C2H2. Number 1. These hydrocarbons. Hydrocarbons, obviously, because they only have hydrogen and carbon in their composition, are very weak acids. Very weak. But they don't have the same strength as acids. If you recall what we talked about previously on orbital electronegativity, I think you can tell me which of these is the strongest acid. That doesn't mean it's strong. These are all very weak acids. But of these 3, which is the strongest? As a Bronsted acid. Relative acid strength. Don't remember?
It's the one on the far right.
That's the strongest acid. Now comes the important question. Why?
Is the most S character.
Well, what has the most S character?
The carbon.
Tell me more. What do you mean by most S character?
It has based on the orbital electronegative thing, it
Well, what orbitals are we talking about?
S orbitals.
Be careful.
Or the sp hybridized one.
How about that? Let's play the game. Here are acids. S strengths. That's the strongest. This is the weakest. All right, this does its acid thing. The hydrogen atoms are equivalent, so it makes no difference which one we consider losing as H+. Same for this and this. Those are the bases. Clearly as bases, this is the strongest and that's the weakest. We want now to have an argument which allows us to understand why. For these 3 bases, this is the strongest and that is the weakest. This carbon, how's it hybridized? SP. This carbon. And at last, this carbon. And so, as we commented before on orbital electronegativity, given that these hybrids are all derived from atomic orbitals from energy level number 2, carbon, 2s and 2p specifically, we can conclude that this sp hybrid has the highest orbital electronegativity of these 3 hybrids, because this thing is 50% s character. And when it comes to atomic orbitals, in a given energy level, the s orbital stabilizes electron density most effectively. We talked about that when we, for example, looked at size trends, radial probability graphs, and found out that these s orbitals have the greatest penetration effect. On a time average basis, they are closer to the nucleus as well as farthest away from the nucleus. So s orbitals are size determiners, or s electrons. Okay? But they're also, these s electrons, the most stable. Because even though on a time average basis they're furthest from the nucleus, they're at the same time closest to the nucleus. Daggone these wonderful little electrons with their wave character. Mysterious critters, but wonderful critters. Critters we have to understand in chemistry, because all chemistry is depending upon valence electrons and how they behave. All right? Greatest orbital electronegativity, 50% s character, 33 1/3% s character, 25% s character. And on we go. So now we know how orbital electronegativity applies. Okay. Now let's add another factor to our list of applicable factors. One you've heard about, although not in this context. Resonance. How do you know when resonance is a valence electron property of a species? How do you know? And the answer is not the teacher told me. How do you know? I give you the formula for a species. What are you going to do to find out if this thing has resonance as a property? Lewis structure. How about that? Wonderful. Absolutely. Okay? There's 4 acids. To which of these 4 acids, or is it the case that it's for all 4? Let's add another one. There's 5 acids. To which of these 5 acids, or is it all 5, or is it some of the 5? Part of the 5. Does resonance apply towards stabilizing negative charge density? Now, we're talking about stabilizing negative charge density for conjugate base. We're considering these things to behave as acids. They lose H+, and we want to look at their conjugate bases and find out how effectively these conjugate bases stabilize negative charge density, in this case as a consequence of resonance. You know what to do. Start drawing pictures. Did you get these pictures? Now, before we start turning these acids into their conjugate bases, oops. Let's put them all in. Before we start turning these acids into their conjugate bases by H plus loss, let's ask the question, which of these acids show resonance? Which of these molecules show resonance? This one? Yes or no?
Yes. Yes.
How many vote yes? This one?
Yes.
Hand up if you vote yes. I'm just writing down a response based on majority. This one? Hand up if you vote yes. This one? Hand up if you vote yes. This one? Hand up if you vote yes. We got 5 yeses. The majority received 40% credit for this question. Because 3 of these choices are wrong. Would you like to refine your decisions? This one? This one? This one?
Yes.
How about that? What possible resonance structure could you write for this? Do you remember that in writing resonance structures, you keep all atomic positions the same, and all you do is vary the degree of bonding electron density at 2 or more bond sites. Vary the degree of bonding electron density at 2 or more bond sites. Look at this picture. Could I just as well have represented this molecule by showing a NO double bond here and an NO single bond here?
Yes.
Resonance. Could I just as well have drawn this picture for this bicarbonate ion, right? By showing the single bond, oops, the single bond here and the double bond here and the negative charge there? If you haven't seen this game yet, but I think you have, for a charge-bearing species like this, if resonance applies, you can do it or illustrate resonance by taking a non-bonding pair from the atom bearing a negative charge and move it to the adjacent bond site. Now, at the instant in which you do this, this carbon has got 1, 2, 3, 4, 5 bonding pairs, and that's impossible. So when you do this, then you're obligated to do this. So that creates this. So for this, resonance. For this, resonance. But not these. You can't play that game with these species. If you do, if you try to relocate multiple bonding electron density for any of these three species, you're going to create an unacceptable Lewis picture. Because you're bound to create separation of opposite sign formal charge. And that's not acceptable, is it, Coulomb? Can't do that. All right? So we looked at the acids. Found out to which of the parent acids resonance applies. Now let's have these things behave as acids. So now we got 1, 2, 3, 4, 5, count them, conjugate bases. To which of these conjugate bases does resonance apply? I'm listening. Every one. So think, if you will, this is a comment to get you to realize this resonance is real stuff. It's, again, when I first heard it, sounds like magic. But it's real. Remember the acetic acid molecule had the H connected to this hydrogen? For the acetic acid molecule, we'll put the H back just for a moment. If you take and measure bond strengths for this thing, which you can do by various methods. You'll learn, for example, about one called infrared spectroscopy in organic chemistry. You'll find that this has a carbon-oxygen double bond and a carbon-oxygen single bond. That's it. These bond lengths and strengths are not the same. This is much stronger than this. This is shorter than this. But when this thing loses H+, and you now have the acetate ion, just as if magic happened, now these bond lengths and strengths compare how? They're identical. They're shorter and stronger in a CO single bond and longer and weaker in a CO double bond. Because it is not the case that we any longer have a CO double bond and a CO single bond. We have resonance stabilized negative charge. Just like we did over there. Same here. For the parent acid, no resonance. But now the NO bond lengths and strengths become equivalent. Exactly the same length and strength. Shorter and stronger NO single bond. Longer, weaker NO double bond. Here we have the bicarb ion now. We already know that has resonance. And here, when we converted the nitric acid molecule to this nitrate ion, every NO bond becomes equivalent length and strength. How about that? Tell me. Because this thing shows resonance, what's the true formal charge on these oxygen atoms? What is it? True formal charge on these oxygen atoms. Is it the case that one's -1 and the other one's 0? What is the true formal charge? -1/2 for each. Because even though we can't make a picture which shows this, our knowledge of resonance forces us to recognize the formal charges of these oxygen atoms are equivalent because the electronic environment of these oxygen atoms are equivalent. That's what resonance gives us. Same here. Nitrite ion. Now then, what are you going to tell me about the negative charge density for the component oxygen atoms of this, the hydrogen carbonate ion? Resonance supply? You betcha. For these two oxygens, but not this one. So, minus a half, minus a half. What are you going to tell me about the true formal charge on each oxygen atom for the nitrate ion? Minus a third. Because by resonance we recognize each of these oxygen atoms to be electronically equivalent. And the whole thing bears a charge of minus 1. None of which is borne by the nitrogen atom. Now we've turned bicarbonate ion into carbonate ion. What's the true formal charge on each oxygen atom? I'm listening. What is it? Minus 2/3. Now tell me, which of these is the strongest base?
Yeah.
Carbonate ion?
Yeah.
Why?
It has the most one.
Yeah, it's twice as minuses, these things. Don't forget the obvious. All right? Now tell me, which of these is the weakest base? Now that, by knowing acid strengths, which we studied back in chapter 18, you should realize what the answer is. But now I want you to tell me why. Which of these is the weakest base?
Nitrate ion.
Nitrate ion. Why is this the weakest base? Well, one comment you could now offer is based on the fact that each oxygen has only got a formal charge of minus a third. That's smaller than minus a half, and clearly smaller than minus 2/3. What else can you tell me as to why nitrate ion is the weakest and most stable of these bases? Go ahead.
HONO2 is the strongest acid among those.
Wait a minute.
HONO2.
We know nitric acid is the strongest acid because it's got the weakest, most stable conjugate base. I want to know why that is the weakest, most stable conjugate base. You see our bag of tricks up here? We know this applies. Anything else apply? What is that?
The second one, the
Electronegativity. How about this? Because is this not an extension of electronegativity? This is like electronegativity being extended through the covalent bond skeleton of a species. Hey, every one of these atoms has got an appreciable electronegativity. So based on electronegativity and induction, you're smearing a charge of minus 1 over 4 atoms. Right? Over 4 atoms. That dilutes the negative charge effectively. So this also applies, doesn't it? How about that? So we're seeing how this stuff fits. Or at least I hope we are. That's what you got to do. You got to let this stuff talk to you. What does this stuff mean? So we look at examples to try to get a better idea of what this stuff means. Okay? And now, the principle of maximum overlap. PMO for shorthand reference. In Chemistry 2045. Oh, back to that place. I expect that you talked about the principle of maximum overlap. But if you did, I do not know the language which the instructor employed. So let's draw a couple of pictures. Overlap of what, for starters? Orbitals. How about that? I have drawn illustrations of the simplest possible orbital overlap interactions. S orbitals with each other, because S orbitals are spherical. Okay so far? Nucleus, center, nucleus, center, nucleus, center, nucleus, center. For which of these s orbital overlap interactions do we find the stronger bond? A or B? I got to vote for B. But I want to know how everybody votes. This is a fair election. Of course, you also know what votes mean on exams. Don't mean a damn thing. Which is the stronger bond?
B.
I got another vote for B.
I'll vote B as well. B.
We got more votes for B. Anybody want to vote for A? All right. This is correct. Now then, why is this the stronger bond?
Greater percentage of the orbital overlaps.
The overlap area. Here's the overlap area. Is a greater percentage of all the orbital space you see than it is here. Are you following me? That's what this maximum overlap means. It's a theoretical consideration, but if the overlap region, for the orbitals which have overlap with each other to make the bond, if the overlap region, or for the case where the overlap region is a larger percentage of all the orbital surface for the orbitals involved, stronger bond. Now why should that be true? I mean, the pictures tell us this overlap region is a greater percentage of the whole picture than is this overlap region, because of the size of the picture. Well, why should this be true? Why should that be a stronger bond? Now let's think again about electronegativity. What does electronegativity seem to depend on? Does it depend on total proton count? As I go to atoms with greater Z values, greater total proton count, do I find electronegativities going up? Do I find electronegativities going up as Z increases? Do I find mercury, for example, with 80 protons to be more electronegative than fluorine? Hell no! How do I find ionization energies depending upon atomic size versus proton count? What counts more? Ionization energy. Lithium, sodium. Sodium, 11 protons in the nucleus. Lithium, 3 protons in the nucleus. Which one is harder to ionize? Lithium or sodium? Which is harder to ionize? Remember ionization trends? Ionization energy trends? As you go down the family, IE, first IE gets smaller. Hey, as you go left to right, in general, first IE gets larger. So ionization energy is depending more on atomic size than it is on total proton count. Well, that means the distance of valence electrons to the nucleus is pretty important. And when I have these small atoms, because they got small orbitals, with nuclei that are this close to the bonding region where the bonding electron density is, I've got a greater stabilization of negative charge density for the bonding electrons than I have here. No more, no less. So I want to leave you with this directive, and we'll pick it up from this point tomorrow. If you've not yet done so, please look at page 2319. See page 2319. On page 2319, you'll see lengths and strengths table of selected covalent bonds. I want you to look at this table and see how covalent bond strength and covalent bond length relate. Okay? And we'll pick it up from this point tomorrow.